The average atomic mass can be a little tricky for students because they confuse it with the atomic mass number. They're not the same thing. You'll want to make sure you've watched the structure of an atom video as well as the videos on atomic mass and atomic number and atomic mass number and isotopes, because all of those are foundational topics that will help you understand this one. So the topic, or the place where we really want to start here, is the idea that not all atoms are exactly the same, of the same type. So we know that the atomic number of an atom tells us its number of protons, and that also tells us the identity of the atom. But what we also know is that the number of neutrons can vary. And because that is the case, then that means my mass number of my atoms can vary. So if you look at this bowl of candy here, you'll see that there are different types of candy in here. There's some M&Ms, there's some Skittles, there's some really big things. I think they might be gobstoppers. And then there's these smaller ones. And let's see. I think I got everything, all the possibilities there. But you'll notice that they're not all the same size, and so they probably don't all weigh the same. So we could think about these as being isotopes. So they're the same type of thing, right? They're all types of candy, but they have different masses. Now, if I wanted to know the mass of this whole entire thing, if I somehow wanted to represent the mass of the candy, I would need to figure out the masses of each individual type and then multiply them by what's called their percent abundance, because I can't just average the masses of M&Ms with the mass of Skittles, because I don't necessarily have the same amounts of Skittles and M&Ms in this collection. So it's kind of like atoms. We might have an isotope that has a mass of, let's say, 10, and every M&M has a mass of 10, but there might be another isotope that has a mass of 8. Right? So that's running around. And then we might have another that has a mass of 11. Okay. And then another that has a mass of, let's make the Skittles 9. Okay? So you can see that we can't say that the mass, the average mass of all the candy is 10 or 11 or 8 or 9, because we've got various amounts of them. So, percent abundance, let's say I wanted to calculate the percent abundance of the M&Ms. The percent abundance is really just the percent. And the reason abundance is in there because it's referencing the fact that this is part of a mixture of something. So if I want to do the percent abundance of M&Ms, then I would need to know the number of M&Ms divided by the total amount of candy. Okay, when we talk about percent abundance of an isotope, of a particular isotope, it's because somebody, somewhere, has gone through and counted, using probably some mass spectroscopy, which is a really expensive instrument, how many of a particular isotope there is. So in our case, we might say the number of 11s divided by the total number of atoms. All right, so once we know the percent abundance of an isotope, then we can calculate the average mass of the candy, or in our case, of an atom. And we can do that by saying average atomic mass. This is going to be a weighted average because I want to account for the fact that I don't have all of the same exact type of thing, and I don't have equal amounts of all the things. So the average atomic mass would be equal to the percent abundance of one type of isotope times the mass of that isotope. Plus the percent abundance of the second isotope, percent abundance number 2, times the mass of that isotope. I could keep adding percent abundances times masses of isotopes for however many isotopes I have. I just have to plug this information in. So let's do an example together. What is the atomic mass of an element which has two naturally occurring isotopes, one with 36.8% abundance and a mass of 13.02 AMU, and the other with a mass of 15.01 AMU? So it's asking me for atomic mass, which tells me that I'm going to need the percent abundance of my two isotopes. Now, I'm only given the percent abundance of one. I'm given that there is 36.8% abundance of the isotope that has a mass of 13.02 AMU. But we're sneaky, right? We know that there's only two isotopes present. So if 36.8% of it is this isotope, then the other percent abundance should simply be 100 minus 36.8%. And then I multiply that by my mass of my second isotope. Now, what you want to think about here is your significant figures, because we're doing multiplication and addition here. So if we're doing percentage here too, so keep in mind that you're dividing your percentages by 100 so that you're multiplying by a fraction. If I take my 36.8 divided by 100% and multiply it by 13.02, my smallest number of significant figures comes from the 36.8. And so my answer from this is 4.79 AMU. And I'm adding that to this number over here, which also came up with three significant figures, 9.49. Notice how this isotope was more abundant, so I end up with a larger number, which is going to be a greater contributor to the overall average atomic mass, hence the term weighted average. Now I'm adding these two together, and when we add numbers, when we add measurements, remember we have to check uncertainties. And so I see that my last significant figure in both cases is in the hundreds place, and so that's what my answer should have. And so I end up with an answer of 14.28 as my average atomic mass, AMU, atomic mass units. That 14.28 also suggests something. If we, for instance, were to look at the periodic table and take, say, for example, nitrogen. Nitrogen's a great example for this. It has 7 protons and an average atomic mass of 14.01. Hey, look, there's my average atomic mass down there in the bottom. Now that we know that that number is a weighted average, then we can say something about how likely it is that any particular isotope might occur for nitrogen. Now, we can't get super specific, but we could make a pretty good guess. Because 14.01 is the average of all the naturally occurring isotopes of nitrogen, we might guess that the most common isotope of nitrogen might be nitrogen with a mass number of 14. That's a reasonable guess given the information we have from the periodic table.